We all drink coffee and tea. And let's say you want to design next generation coffee mugs, tea mugs, which can sustain the hot coffee for a very large amount of hours. So you want to design an efficient coffee mug or a tea mug. What kind of questions you would concern yourself with? So I'll write 2 questions here, and you have to decide which one would you select or which one would you focus on if you are a thermal engineer or someone who is interested in designing a mug. How much heat is transferred to the surroundings? Question number 2. How long it takes for the coffee mug to lose its entire heat to ambient or to come in equilibrium with the ambient. So one of the questions belongs to the field of thermodynamics. One of the questions belongs to the field of heat transfer. Can you tell me which one belongs to which one? So question number 1. Thermodynamics, right? And you see what's happening here. It's talking about how do we go from one state to the other. So it talks about extremes. We are at a hot state where we keep the coffee mug, how much heat is there, and then how much heat it lost. In thermodynamics, we do not talk about the transient, what happens in between. So this is your question for heat transfer, and heat transfer is concerned with transient or out of equilibrium systems. Out of equilibrium driven by temperature difference. Right? Coffee is at high temperature, ambient is at lower temperature. So you will have this transition between one equilibrium state to other. And this transition is what we try to capture from heat transfer. Right? Now, another type of question that you might be concerned with is that if you want to design a good mug, you might want to look at where is the heat leak. From where, so it's a closed mug that you're carrying to your work or lab or office. And you might want to know kahan se or from where the heat is leaking out. Right? And you might want to look at the temperature map within the mug. Yes? That would give you where is the heat flux coming out. Yes? That's going to be 0. I can take this on the other side and then write delta U system is equal to heat plus work. I can decompose heat by the surroundings or change internal energy of the surroundings into Q and W, meaning into system, heat into the system, which is on the system. Now, with this, what we can do furthermore, in this course, we will be concerned with non-work systems that do not perform. For example, that coffee mug, right? It did not start moving. This is just losing its heat to the ambient. Any change in internal energy is captured by Q. Yes? Now, we sort of get it, okay? Then heat is a form of, or it conveys how much change in internal energy is there in the system. Yes? Heat conveys. So how much of, like, this X amount of heat or Q amount of heat will be in the system, that much delta U system will change. Yes? Now, you have all done thermodynamics in your high school. When was it? In 11th or 12th? the heat and borrowing it from the surrounding, giving it to the system, raising the internal energy of the system. But what exactly is happening? You see the water moving? When we make tea, we see the water moving, right?
Kinetic energy of the molecule.
Kinetic energy. So there is kinetic energy, meaning associated with the movement of molecules. Right? If it is cold, they are just sitting like this. If you heat them up, they vibrate more vigorously. We also call it sensible heat. Just some words. What is the other kind? Latent energy is one kind of it. So let's call it latent. What does it concern itself with?
Change in phase.
Change in state itself. So now something was in solid state or liquid state, converted to gas state. So this is associated with the molecular vibrations. Am I audible at the back? I didn't put the mic. Should I put?
Yes, sir.
And the other is associated with phase change. Hello. Hello. Yeah. You can hear me, right? Is it better? Okay. Now let's go even further. So in this course, what we will deal ourselves with is this kinetic energy aspect. And let's ask ourselves, is that if a specific amount of heat is given to the system, right, it results in what? How do we measure this Q? How do we quantify if a system is hot or cold? We need to have some measurable instrument, right? So that common instrument is called thermometer. So if let's say you are performing an experiment and you heat the system under control and it's perfectly insulated so that you can measure the temperature accurately. So now we measure heat via temperature. Yes, but we also know this, that if I take water and if I give it some amount of heat, it will result in temperature change. If instead of water I took honey, would it lead to same temperature change? If I take wood, would it lead to same temperature change? Right? So we also intuitively know that different materials require different heat to yield same delta T. I've just reversed the argument. If you want to cause a delta T change in temperature, different materials would require different heat. Yes? captured by a specific heat given by something called CP. But let's come to it more organically. So if you were to conduct these experiments, let's say, how would you come about an expression? Because see, we are focusing entirely on sensible heat. We conducted experiments. We took water of 1 gram, let's say, and then what would we measure in such an experiment? Temperature change, right? So basically, what an experiment is, you keep the system in observation. You change one thing at a time, right? So the sensible heat, if you can imagine this experiment, let me write it as Q. What do you see proportional to? Obviously, delta T. What else? Mass, because here I'm talking about 1 gram. If I take 2 grams, it would require double the heat, proportional to M. And now, if you want to combine it all together, Cp is what forms your. Some books also write as C. So this is your expression for sensible heat. What are the units of Cp? If the units of Q is joule. This is kg. This is Kelvin or Celsius? It doesn't matter. It doesn't matter. And it is also source of most common mistakes. One of the most common mistakes in calculation of Cp. Now can you tell me what is the unit of Cp? Joule per kg Kelvin, or joule per kg Celsius. I've seen a few mistakes in the last year batch where I have given this value in joule per kg Celsius and they converted by multiplying with 273 to convert it to Kelvin because that's what they think is correct. So don't do that mistake because delta T is what matters. Delta T in Kelvin, delta T in Celsius is the same. So now with that, we know a bit more about heat. Now let's go back to the times when this concept of calorie was, defined or agreed upon. So it's like distance, right? To measure distance, so people measure distance in yards. Throughout the history, we have measured in different ways. We said, okay, this is 1 meter, and now we'll measure everything in these meters. In the same way, we said, this is 1 calorie, or this is the notion of specific heat. Now we're going to take this as our base and measure every other material's or every other material's specific heat in this manner. Yes? Why did we do water? Because it's readily available. It's the most available item, and also we'll come to that it has one of the most highest specific heats. Okay. Now, so let's go back in time and say that we know Cp of water, or we have devised that it is going to be 4.19 kilojoule per kg Kelvin, right? 4.19 joule, but this is 1 gram. I have to convert to SI units of kilos. So now if we use this to measure the specific heat of gold item that I have, it is of how much grams? 100 grams. So I have this 100 gram gold and I want to measure it specifically. How would you do this?
We'll give the same heat to both of them.
What is both of them? So you know water and you have this chunk of gold. So just imagine it looks like this. Now what do we do?
We'll give the same heat to water and gold and we'll measure the delta T. And from that we
But how do you measure the heat for this? You don't know the Cp of this.
Gold into the water at some temperature and then you like calculate the change in the temperature, like the high temperature, and then from you calculate the
what he said for everyone, in order to measure this gold specifically, we would take some water in a tank which is insulated, and then we will bring this gold there. Maybe we first heat it up, and then we'll measure how much.
We will let the temperature settle for the fire temperature, and then we'll calculate the changing temperature for water, and which is the heat then obviously goes to the gold.
Yeah.
So
Excellent.
CP and then
Excellent. So we'll do that. So this is called, this apparatus is called calorimeter, also known as bomb calorimeter. Have you heard this bomb calorimeter? Do you know why it's called bomb? Because it explodes. Because it was made by someone named atom bomb.
That vessel is called the bomb.
Bomb. Why is it called bomb? Because it's constant volume. Whenever you do a change or chemical reaction or something and keep it confined, that's called a bomb. But in case of actual bomb, it explodes. So this is for the constant or constricted volume. Okay, so we insulate it because that's very important. If you don't insulate it, how do you reliably measure the temperature change? What's your name, by the way? So we will bring, now first we have to heat it up. How would we heat it up? And we should know that temperature. How would you heat it up? So you will put it, so you are in 18th century, by the way, or whenever this was designed. 19th century. How will you will flame it up? Because you can't insert thermometer.
Maybe a large reservoir of water or something.
Large reservoir of water, so and we let it go to equilibrium. So we maintain, we give the flame here, okay, and then we let it go to 300 degrees Celsius. Let's wait time to equal to infinity, meaning long enough time, so that we are sure that this is the same temperature as the bath. Okay, now what do we do?
then we will put this bar into some another reservoir like in this end.
So we will place this here, and then this already has water. So let's say it is 1 kg water. So let's say it is at the room temperature currently 14.5 degrees Celsius.
And then we will note the steady temperature.
So we know, so we have to first note down the temperature at early stage. Okay, so let's start our initial time period. CP of gold is unknown. Mass of gold is known, 0.1 kg. What else? T of gold at start is known. How much is it? 300 degrees Celsius. In case of water, we know CP water is 4.19, but it's in kilojoules, so let me write it. That's 4190. Mass of water, for convenience, we will just take 1 kg. T water is initially at 14.5 degrees Celsius. So I'm just writing in tabulated form what I've already told you. Yes? Now we'll conduct the experiment.
So then
What will we do in the end?
we will find the temperature of that calorimeter, and we will
So there must be a thermometer. No? So we'll measure, so then we have to write down that. T of water, so let me write I, initial, and then N. N is, let's say, 15.5 degrees Celsius. Easier. Huh? Just 1 degree rise has happened. What do we write for gold as well?
same temperature.
Same thing. And gold is 15.5 degrees Celsius. So heat loss should be equal to heat gain because we believe this insulation is perfect. So we can just, can you do that and use your mobile phones if needed or calculators to do the calculation. So you have to just do mg cpg delta tg and water cp water delta t water. We know everything except this. So can you tell me what is this in kilojoule per kg Kelvin? And then we move to the next question.
One
47 point? 147.27. So in kg, kilojoule per kg Kelvin, can I at approximately 0.15? Although in exam you should be more precise, but what I want to focus here, it will make sense. So I want to focus on the rough value, 0.15. Everybody got it? Shall we move forward? Or do we need time? Okay. Now, a further question now. You do this experiment and your friend tells you that actually Cp of gold is known. That is also known. People who did this also did for gold. And the value for that is 0.13. Not the same as this. I'll give it to you. So you perform this experiment in your lab, and then like 100 other people have performed it elsewhere, and their value, 1,000 other people, so that you know they are not wrong. And the correct value seems to be for pure gold. This is pure gold. CPPG, pure gold, seems to be 0.13 kilojoule per kg Kelvin. I'm not sure exactly how much is pure gold, but for the sake of this discussion, so there's a material and people have done properly, and it is found to be for that material purity 0.13. Now, what would be the potential reason for you not getting the correct answer?
imperfect insulation.
Imperfect insulation. So can I know why? Wrong answer. So reason number one comes to mind is imperfect insulation. Any other reason?
Yeah, there could be impurities in the gold.
Impurities in the gold. And is there anyone here who can tell me which one is correct? Huh? We don't know. So, or how many of us think there is no way we can ask this question as of now? We cannot answer. Who thinks we can answer? You have to think. The answer is you can answer. Now let's perform a simpler experiment. Let's take this experiment and break the insulation even further. Let's destroy your experiment, sorry. And we'll remove further insulation and make it somewhat insulated. Okay? What do you think will happen to the values? And then let's do the calculation and let's observe the trend. That's all right. So again, so it was initially at the room temperature, 14.5. So now let's say instead of 15.5, it will become
A bit higher.
15. No, we didn't break this insulation completely. It's still there and it seems to stay. So let's say there is some mistake in the experiment, i.e. imperfect conditions. So this became 15. Can you do the calculation? Tell me what is the CP that you get? This time it is basically imperfect conditions.
Point 073.
Instead of this, what?
Point 0735.
0.07
35.
kilojoule per kg Kelvin. So what happened? The further imperfect conditions reduce the Cp to half. Yes? Why didn't you get the answer to be double 0.3? Yes? So now can you answer this question? Yes.
Sir, the final temperature would depend on the surrounding temperature, right?
Yes, but I'm saying due to imperfect conditions, let's take that we could not measure it properly. We could measure even worse than before. We measured 15. I know what you mean that if the ambient is at 14.5, it eventually will go to 14.5.
No, like if it is at higher temperature, like 25 degrees Celsius.
What is it at?
Ambient surrounding.
No, but I'm telling you that in this problem it's at 14.5. That's why we took the water, right? At 14. I had mentioned at the start of this. Now, yes, so what has happened? The Cp, what you found out is half, but it has decreased.
So it should be impurity in gold because insulation leads to a big impact.
It could still be anything. And what's your name again?
Anisha.
Anish. So, that's correct. The reason is impurity of gold because any imperfection in insulation would result in estimation that is lower than the actual value. Isn't it the case? if let's say as you what's your name again? Come on, that was a good question. So let's say if we were going back to the equilibrium and this became 14.5, what would your Cp look like in that case? 0. What does Cp of 0 mean? So let's say we had very poor insulation or almost poor insulation, the Cp would apparently look like 0. Cp 0 means material has no heat capacity. So if let's say you had a jar and you put that 300 degree hot gold here, it will not yield in any temperature difference. Yes? So estimation of temperature rise is going even further. The estimation of Cp is going even down. So in no way you can have Cp more than the actual value because of imperfect conditions. Yes? Is there any question? Okay. With that, let's just imagine a condition where Cp is infinity. What would that mean? No change in water. No change in water or infinite change in water? If Cp is infinity and you do this experiment, the water temperature would become right. Should. So let's see if that happens. mCpG delta T, this is infinite. Although it's not really possible.
Temperature of gold will not change. Gold temperature will not change.
This is Cp of water or gold? Which is infinity.
Cp of gold.
Cp of gold.
Cp of water or any material that has infinite heat, then that delta Tg will become 0, right? So you have a condition where it is infinity to 0. It's coming infinity because on the other side when you take it there, it is apparently 0. So basically meaning that your temperature, if it's very high specific heat, your temperature of the container will rise to the temperature of the material when you inserted it. Yes? This is just something to think about so that you know high specific heat ka matlab kya hai.
So but then doesn't his point come into play if you're saying that an imperfection in insulation has to cause a lower Cp, but if the ambient temperature is say much higher, then wouldn't it cause a higher Cp?
If the ambient temperature is much higher,
Like if the water is at 15 degrees Celsius and say the surroundings are at 35 degrees Celsius,
yeah.
then wouldn't an imperfection in
But then
insulation?
I would take this as so you can repeat the the exercise is when the ambient temperature to start with is 35 degrees Celsius.
So then you would start with
35, and then your measurement would not be 15, it would rise to something different. Your CP would come out to be the same.
Okay. So initial temperature of water is the ambient temperature.
Yes, initial temperature is what is given. I took it as 14.5 because the definition had 14.5 and it's currently quite good. I could have taken it 25. So in exam, when next time I'll ask this question when the temperature is a bit high, I'll put that temperature. Okay, so now we have our bomb calorimeter done. Yes, so with that, can you turn your attention to your mobile phones? Yes. And I've uploaded on Hello IITK some lecture companion material. In that you will see a table, and a graph for CP. So I'll give you values of CP and a trend of CP. So first, let's go to the values of CP. There is a general trend that metals and semiconductors are in a similar lot, which is the material that sticks out, which has the highest CP. Which material has high CP? Water. Any reason that you think that might be? Because when you heat a material like water is made of H2O. It has hydrogen bonds. One bond breaks, it forms another one. So it is very resilient. It can store large amounts of heat. It is also one of the reasons why most industries use heat storage material as water. So let's say you have an exothermic reactor producing a lot of heat. If you want to store that heat, you would just heat up some water and then use that water to heat up something else. You wouldn't want a low heat capacity material to store your heat in. Right? You wouldn't want same amount of heat generating a lot of delta T. So in other words, if you have two options, if you have water and let's say some polymeric solution which has a lower CP, the polymeric solution has lower CP, meaning same heat will yield to a higher temperature or lower temperature. That materials which is not water, its CP is lower. Q amount of heat that was given to water, will it result in a higher temperature? Much higher temperature if it is much lower, right? I mean, water is clearly way above the rest except seawater, which is again water-based water. So now, do you see problems with this if you choose any other material than water as specific? Because then we have to insulate it. Otherwise, then it will go to surroundings. And insulating something at higher temperature is much less desirable than insulating something at manageable temperatures. So these are the reasons why water is used as a heat storage material. It's cheap, readily available. In figure 2, you see that even in water, when it goes through this phase transition, ice, liquid, and gas, which one is the highest? Liquid is highest and jumps up because of the mobility of water. In solid state, the ice crystals are fixed. So if you provide heat, they cannot move elsewhere and make new hydrogen bonds. Same goes for, different reason for gas. Gas is a very loosely packed, right? This vapor is very loosely packed element or material. Any material that if you break the hydrogen bond, it has to travel a bit further to find another hydrogen bond. Whereas in liquid, it's a nice mixture. You have all the nearby hydrogen bonds. I hope it makes sense. Now, all this exercise that we've done is for CP. It's more of a thermodynamic thing, but we'll be using Q dot, Fourier's law. Q is there, MCP delta T will play a major role. So CP is important to retain in a minute. Let's move on to the spirit of heat transfer, which is transient state. How heat changes over time. So this is the first concept that you should remember, that accumulation of heat is given by, or rate of accumulation of heat is given by, I should just write Q, right? Because anyway it's a transfer of heat. Q by delta T would give you idea about this, let's do another question or an example. Imagine you have a glass kettle here with you, and I'm not your heat transfer instructor, but some layman who doesn't belong to chemical engineering. And what they want is to heat this. Okay, so let me write. You have a 1.2 kg capacity or gallons or whatever, and it's made of, you have those fancy ones, it's made of ceramic material or glass material, and this is 1.2 kg, meaning this glass kettle will contain water of 1.2 kg. You fill it to the maximum, and this layperson asks you that how much time should I wait for my water to go from room temperature to 95 degrees Celsius. So, how much time is needed to reach 95 degrees Celsius, and the room temperature in this problem, I'll tell you. In this case is 15, let's say. How would you calculate it? I'll not give you the values because they are anyways a big hint to how to solve the problem. So if there is, so this person is having a chat with you, and then all you have is a connection to internet, although currently it's not very good. How would you answer this question? And you can search anything on the internet. By internet I mean me. You can ask me that you need anything to solve this problem.
What's the wattage of the?
What's the
Wattage.
Yes. 1200 watts. Excellent. Huh?
It's easy, we can calculate the time. We have to know the heat capacity of water.
So Nicole, it's easy one.
How much water has the person?
1.2 kg water. Do you have all the information with you? How much ceramic is there? That's a good question. Ceramic, you can take it as 0.7. So Cp ceramic is 0.7 kilojoule per kg Kelvin. नहीं 1.2 kg capacity है. I'll tell you the mass of this. You can take it as M kettle as 500 grams, so 0.5 kg. That's a good observation. What's your name? Arpan. So it's, I mean, you can do the calculation on the basis of water, but again, it requires a certain attention to also include ceramic in your calculation, right? Because if you do this and then I'll ask you the second question. So what is the time required? What do you have to do, by the way? It's quite easy, right? I've written it there. Yes. So this is given by, this is given as 1200. So basically you have 1200 watts is equal to heat by delta T. This is equal to M1 Cp1 delta T and then M2 Cp2 delta T. Is delta T same for ceramic and water? Yes. Room temperature to 95 degrees. So you can do this, right? You're out of time. Now my question is, if we were to change this ceramic to iron, would your heating time change?
Yes.
Yes. So would the design of a kettle require some idea about the Cp of the material? What is made of? Yes. That's it. With that we meet tomorrow and start production.